Another thing I've learned is you got to let it finish this thing, and then you can go away. Fluid mechanics. There. Now, the light's really bad. Okay, there's no reflection. There is a reflection. There's that bulb. How do I get rid of that one? Okay. Oh, there we go. All right, if y'all don't mind, I'm just gonna step out in the hall and take a drink of my energy drink. And then I'll come. What is that? Oh, okay. And then we'll come back and work some fluids problems. All right, this bar here, I never was able to get that bar off of there, was I? It's just in the way. Now what does this do? It's a deer up on the screen. You know what? Oh no, I gotta go this way. Okay. Well, let's go ahead and do something here. I have everything. I think I do. Okay, so what I'll do is I'll do a turn this together so that it doesn't look like it's turned, but to me, is that viewable up there? Hey, where am I? All right, so we already kind of went through this. I'm not sure why I'm all the way back up here. Maybe I was just moving around. So let's pick off another problem here. And then next time what I'll do is pick off the problems that are in the homework. So there's a problem. You know, two pipes are connected as shown in that picture. Just had to make sure that my pictures, the words are. So he wants to know PA minus PB. Actually, I'm not sure I really need to copy the text. So I'm just going to do the picture. And looks like I may have to add a page. I don't know what that's doing there. Okay, so I'm going to put it about right there. So he wanted to know, I don't know if it was PA minus PB, or you could just say what's the delta P. But what I'm going to do is I'm just going to pick one. And so all you do is your concept here is to just pick a spot. I'll start with PA. Now, what you really want to do at the Cracker Barrel, you start, and you know you're going to end up there. So you know you're going to end up there. Well, how did you get there? Well, first thing I did, now I'm going to be kind of ridiculous to start with, because if you're at Cracker Barrel and you're doing these, or wherever, and you're doing these things, you got to follow all of them. So here, I go up, then I'm going through this fluid, which is water, and I end up landing right here. Now, there's two things you could do. One, you could label every interface, and I'll do it maybe I'll do it that way first. So if I were going from B up and then back down, and I ended up here, what I would have been doing is I would have gone up effectively this far and back down that far. Now, you don't know this distance right here, but what you do know is you know that this distance is 1.3 meters minus the 0.5. It seems like a weird thing to do, but it works to wear this glove because it's a touch screen. So if it wasn't a touch screen, it wouldn't be a problem. Because now I can move my hand all across it and it doesn't behave. Oh, so I say. But it's less sensitive. Well, maybe I'm just fooling myself. Okay, never mind. So here's 0.8 meters from here to here. So essentially what I did is I took off, I went up to here, and then I went up here and back down to here. Now I think I'll label this 1, and I think somehow I erased it. So think to yourself, when I start here, I started at B, and then I went up, and when I go up, I decrease pressure when I'm going up. So up is equal to minus, well, try to put quotes there, and a down is equal to a plus. How far did I go? I went a certain height through a certain material. So that's the height you're going, and that's what you're going through. And it's that simple. And then when you arrived at P1. So that's all there is to it. I went up. So in the process, if you see a minus, you'll... Anyway, so now I'm going to start at P1. So I'm starting here. I swam down that far, and then I just kind of swam across. Turns out those are two at the same elevation, so I swam down. Here, I should go ahead and call this 0.8. And this is in SI, so that is 9810 newtons per meter to the cube. And let me talk about that in a second. So I went down a certain distance through a certain material and arrived at P2. Now it turns out, how far did I go? I went 0.6 meters. And what did I go through? Now, okay, this is specific gravity. Now you have to remember back, gamma of some, I'll call this GF for gauge fluid, is equal to the specific gravity of the gauge fluid times gamma of water at 4 degrees C. Now I guess I'll talk about the water. Well, let me finish this, because this is 2.6 times 9810. And so that's the gamma there. It's a heavier fluid, so it, went to the bottom. Now, let me address this for a second. Gamma is either 62.4 pounds, or in this book, the units we have in this book, per cubic foot, or if you want to get into the other now rho 1.94 slugs per cubic feet. So you multiply this times 32.2 and you'll get that number. Now it turns out water is a special substance because they made the SI unit, they structured it so that this occurred. Kilograms per meter to the cube. Now, gravity, 9.8. Some people carry more digits. The problem with that is gravity does change quite a bit. You multiply those two together and you get that. So I always remember that. So I never really remember that. I always remember 1,000. I mean, it's kind of dumb, but that's the way I remember things. So, and this is for water at 4 degrees C, and same thing. So those are the reference values there that, by the time you get done, I mean, you don't have to memorize those, but memorization just naturally happens sometimes with stuff like that. Because most fluids out there are water anyway. So the last stage, and we'll finish this up and keep, what I'm going to do is I'm going to take these and line them up below in a minute. Okay, the next stage, the guy swims up again. He starts at 2, he swims up, and in this case, he's swimming this far and this far together, but I'm just going to call it H. And he's swimming through gamma. This time he's back swimming through water. So, and he arrives at PA. Now, really what I should do to be proper is I'm going to do this. Let me fix this up a little bit. Okay. So I'm going to call this H1. I'm going to call this gamma 1. So actually, it should be H1 and gamma 1. Now, I'm going to call, there of course is still 1 and here's 2. I got rid of the 2 for some reason. The next step I'm going to take H2, and then the final step will be that distance, H3. And we'll call this gamma 2, which we know what it's going to be. And we know this will be gamma 3, which we know gamma 3 and gamma 1 are the same thing. But that makes it so that I can put subscripts on here and identify that these are actually different gammas. And here's the reason I do that. I'm going to copy these 3 equations. The first one, and the second one, and then the third one. PB minus H1 gamma 1, we'll put the numbers in there in a second, plus P1. Right under it I'll say P1 plus H2 gamma 2 is equal to P, ended up being 2, right there, that location right there. And then this last one, which is P2 minus H3 gamma 3, hello, gamma 3, okay, equals to PA. Now, if you look at those 3 equations, you're sitting there looking at them and you say, hey, I got a P1 there, P1 here, I got a P2 here, and I got a P2 there. the way I generally resolve that is I move that to the left side. If you do that, it becomes this. Now move this one to the left side. If you do that, it becomes this, and now add them up. First thing you find out is this thing cancels that one, and this thing cancels that one. So what happened here is I could take this in a one fell swoop. In other words, I could go down all the way to A. In other words, I started at B, I went up H1 through gamma 1, then I went down H2 through gamma 2, then I went back up H3 times gamma 3, and I arrived at PA. And just like that, it's like, those little mazes, that's what they're called, little mazes at Cracker Barrel, or I think they have them also at IHOP and places like that. So you can find those all over the place. So that's it. So now it's just a matter of sticking in the numbers, which is a tedious, unfortunate thing. I can take the PB and move to the other side, and then I would have PA minus PB equal to, and I'm going to list that one first because it's positive. Uh-oh. All right, arrive back. So H2 was the funny gauge fluid, I think. So it was 2.6 times heavier, and that's what that's saying. This is 2.6 times heavier than water. And that's the key. These terms are kind of weird. So this is 2.6 times heavier than water. So that's your gamma. I forgot the height. H2 was 0.6 meters. And then H1, this and this were both water. So H1, what was H1? I forgot already. 0.8 meters. So 0.8 meters times water, you're going through water. Why did I write that 8? And then you went up again through water, but this time you went this distance. It was 1.1. Okay, so now you could break off these little coefficients and then add those, just because since you referenced water, you get 0.6 times 2.6 minus 0.8 minus 1.1, and whatever that is going to be your delta P. And so that's the whole thing. Let's go back to the book and look at it, because I've already hacked up on this thing enough. And you can look at all of them that way. Okay, so if he's obviously given you, let's just look at this one, for example. He's obviously given you some pressure here. So he probably wants to know the pressure there. Determine the pressure at B. Okay, so what you could do, you start here, for example. And then I'll call it PA because that's what he calls it. I go down. Oh, but wait, I come right back up. Oh, wait, so that's the same pressure. So this is equal to PA. Now you could write a spot 0 there and say PA plus nothing is equal to P1, or you could just recognize that and say, hey, I went down, and every time I go left or right, there's no change of pressure, but when I go up or down, there is. Went to here. The next thing I do is they go through this little bit lighter fluid than water, like an oil or something. So if you pour oil inside water, the oil kind of floats on the top. It's kind of, and that can be problematic. So now, yeah, I go up and I decrease my pressure a lot, but then I go back down the same distance, and this pressure right here is the same as the pressure over here. So believe it or not, this is still PA. Now I'm continuing to go down. So I got PA, and as I go down, I'm increasing pressure, and I'm going through this funny fluid here, and I'll say specific gravity of 0.8 times gamma of water times the height, which just so happens to be 3 meters here. So again, this is your 9810. And now I'm kind of arrived there. Now I could stop and write the equation, or I could continue my journey and go down. I'm going down 2 more meters. This time I'm going through water. So that's pretty cool. So that's my H. And then my gamma H2O. I'm lining this up weird. 9810. And where did I end up? I ended up here, but I could swim this way. Didn't change the pressure, but I ended at PB. So if you think of it, now the other thing to think about is, and this is the thing that catches people, what happens when you have a bubble? And this is pretty important, especially if you're using these to measure things. And let me see if I can find one. You've got to have one in there. There's one, but you're not going all the way through it. Okay, well, I'm just gonna make one up because I think that's a pretty important problem. Let's say you're in lab 2 or whatever, and you got this wind tunnel going over there, and what you've got, or the pipe problem. The pipe has the same. The pipe actually may be worse. So there's a big pipe going down there. There's water flowing really fast from left to right. And what you want to know is you want to know P1 and P2. Well, it turns out in reality what happens is, in order for the water to go from left to right, this one's got to be slightly bigger than that one. And so what do? You just string a manometer off there. But let's say we wanted to do something silly. And what we wanted to do, I don't know how to flip this, but I can sure copy it down. And we decided we wanted to do this. We had, for some reason, this pipe is near the ground, say. And because it's near the ground, I can't put anything below it. So what I got to do is I got to put something above it. And so I do something like so. I got to make sure But it just so happens that some air bubbles get stuck in there. And so what happens when you have air? Well, let's say you had a bad bunch of air. So in other words, this is all air, and you're like, I can't get the air out of there. What do I do? So basically, I'm going to use it symbolically, if you're okay with that. H1, H2, H3, and then, what do I do? Go across to here, call that H4. So what I'll do here is I'll call this gamma, say water flowing through here. So this would be gamma 1, which is water. It would be gamma 2, which is maybe something heavier. So let's say the specific gravity here is equal to 2, just so it won't be water. Okay, so gamma here is almost equal to 0. Not technically exactly equal to 0, pretty close to it. And your gamma here would be, say I've already used 1, used 2, so this has to be 3. Now, so what do you do here? Well, let's say we just start here. We're going to want to end here. So we're starting at P2. And here. The book, he has stuff like this, so I'll make mine that way too. Blue is a lot of water. So here's your water. Here's your water. Here's your water. Green is the heavy fluid, and air sometimes doesn't have any color. So I'm just leaving that one colorless. So let's say we start our journey. So we start our journey at P2. I'm going to start there. I'm going to head up and take stock of things. So I'm heading upwards. I go that distance through that fluid. Now, the problem is, technically, let me slide over. Technically, okay, this doesn't look like it, but technically, I do go down through air, but this is almost zero. So if you get an air bubble in your line, you can really mess up your pressure reader. So when you're taking lab 2, I guess it's, I don't know. Anyway, when you're taking that, what you do is you try to thump it. You thump it with your finger to get those bubbles out. You shake it sometimes, so you know. So if you look through the manometer tube, you want to try to get the bubbles. The thing is the bubbles, they can have this ability to stick in there, so you can have sometimes air bubbles sticking there because of the surface tension between the air and the water or whatever. But we all have water. So that's something to pay attention to, because if it was very small and you didn't, you would have the wrong number. So we got to this point. Now we're going back up. Going up. We went down here, but essentially we went through air, so it really doesn't matter. We went back up. We went up H3 through gamma 2, and now we've entered into water again. And so we do go up, so we go to here, and then we continue back down. Continue back down, is it H4? Yeah, it's H4 through gamma 3. And we arrive at P1. Oops. We arrive here at P1. And that's essentially it. Now, this is the part that I've seen catch people off guard before. You got to be real careful about that. It's like an accounting thing. You got to make sure you account for everything. If you're not careful and you just throw it away, now of course in this particular case you can throw it away, but systematically in your mind when you're going through it, just go through the manometer from one end to the other. That's all you're doing. Going up, you lose pressure. Going down, you gain pressure. The pressure you gain is basically the gamma times the fluid you're going through. And that's it. That's all there is to it. Yeah, that's like if you put in a cubic foot of a aquarium. I'm trying to think. So say you had a foot cube, an aquarium that was a 1 by 1 by 1, then water would weigh 62.4 pounds, roughly. Depends on the temperature a little bit, but not that much. And that's the one that's this for newtons per cubic foot. So if you look back at the book, you'll see rho times g, where that is, the density or is equal to the mass per unit volume. Well, if you just multiply mass times g, that gives you your weight. So that's where this is. There's so many specifics in here. You got specific volume, which was before. Now you got specific weight, and then you got specific gravity. One way to remember it is there's this thing called SG, and luckily he it's specific gravity. So if you don't see a SG and you see something specific in here, then it's usually specific weight, and that's just the pounds. Well, it doesn't have to be pounds. It could be newtons for this, but whatever it is. But what we found out before is if you want to find out how much you increase your pressure, it turns out, and there are a couple ways you could approach this, but one way is, say you took a piece of square and you said, I want to know what the pressure is that this is 10 foot underwater. Okay, I'm trying to draw. So if it's 10 foot underwater, it looks like that. So I want to know the pressure there. Well, let's just imagine that's a 1 by 1. So if that's a 1 by 1, then the whole volume here is a 1 by 1 by 10. That's the volume. How much does that weigh? Well, gamma is since I've chosen this to be units of feet, I'm going to say it's 62.4 pounds per cubic feet. Well, the volume is in cubic feet. So if you think about it, the total weight of that column of water is 624. Because I multiply, 1 times 1 times 10. Well, that's the total weight. But it's over a 1 by 1 area. So it turns out that it's 624 pounds per square foot, which comes back to the point where the pressure increases like this. As I go down, I'm increasing pressure by that amount. Of course, if I come up the same amount, I decrease the pressure. But as I go down, it's heavier, it's higher pressure the deeper you go. Which is why, submarines can go to a certain point, and then it gets to the point there where it can actually crack them and collapse them, You've seen those deep diving things where the guy gets in there and it's like something like that. It's all spherical. It's got like all these bulkheads and big metal around it, in a little bubble so he could see the crazy fish. That's to offset the pressure, if you think about it. I mean, this is pretty. Seawater's a little bit heavier than this, but let's just assume we're going we're going in the lake, and we're going to go down. Okay, there isn't a depth of water at 5,000, but I think the Marianas Trench is like a mile deep. And so you start looking at that. Oh, I don't even know. Do I have octave? Oh, I think I do. Wait, I think I just passed it. So 5,000 times 62.4 is 312,000 pounds per square foot. So if you want to get it in something that you're used to seeing, I should have put it in here. You could go in and say, okay, let's see. Oh, and we're going back there. Okay, wait a minute. There. So take that number divided by 144. It's 2,166 psi. That's a lot. Anybody a scuba diver? If you're a scuba diver, this concept is similar. So here you are. Okay, I'm not a great drawer. So here's your frog feet, and you're swimming along, but you got these lungs that you got to breathe through. Okay, all right. So this is not a good picture. But anyway, here you are. But now you're not swimming at that depth at 5,000 feet, but you're swimming, say, at 100 feet. 100 feet is pretty reasonable. So 100, what did I say before? I said 5,000, didn't I? So 100 times 62.4, let's move the digits twice. And so that's pounds per square foot. Did I move the digit twice? Once, twice, yeah. So, assuming your lungs is a square foot roughly, which it probably is a little bit less, that's 6,000 pounds. The pressure on the outside of your lungs, if you were holding your breath, it would offset itself. In other words, if you hold your breath and you start going down underwater, what happens is the same thing that happens if you take a balloon and do that. The balloon's volume is like this, and it starts shrinking because the pressure gets greater and greater and greater. Well, to offset that, you can get a big, long snorkel, right? And that's 100 foot under there. The problem with that is this is atmospheric. So that makes this pressure, gauge pressure, equals 0. So it's not possible. You can't take a garden hose and go jump in the water and start swimming down without like your lungs collapsing and stuff. So what people do is they attach this big cylinder, and usually it's pressurized up to about, it can be as high as 3,000 psi in there. Not because you need all 3,000, but because you need enough supply air to swim around. And then you got this funny thing here, a big globule that's a regulator, and it goes around your mouth, and you got this little thing that holds on it. What this regulator does is kind of senses the pressure out here and says, hey, I got to match the pressure go into this guy's mouth of that same pressure it's out here. And so you got to make sure your regulator works, and there's some dials and things on that. If your regulator works fine, you're going to be fine. As you go down, it adjusts its pressure. Now you can, even with that, if you move quickly through the pressures, you can get the bends or a nitrogen deposit in your. I've heard, I don't know this to be the case, but I've heard people that starts bubbling inside your body if you don't, if you don't do that correctly. So the big deal here is that, and that's what you're using as you're doing these manometer problems. You're starting at the low pressure or a pressure. Then you get less pressure as you go to here. And then through the air, nothing happens. And then, yes, you get more pressure as you go into here, but then suddenly you come up to right here, it's the same elevation there. And now you're getting less as you go up. So as you go up, you're getting less. And then, yes, you go up, and then you come back down the same level. And now, from this point, you're swimming down, you're gaining pressure. So just think of it as that's all you're doing, is you're just going up and down through there. But he did not, he had some with air bubbles in them before in the problem set. I don't know what happened to them. Maybe it was a different edition. So this is the biggest problem I see, is that people forget the air bubble, or they'll make an assumption and jump right over the top of the air bubble, But if you just think of it as a puzzle at Cracker Barrel, where you're just going through a maze, and when you're going through the maze, when you go left and right, it doesn't matter. When you go up, you're decreasing pressure. When you go back down, you're increasing it, and you just track it. How far you went? What did you swim through? How far did you go? What did you swim through? What direction? So you only have three things: up or down. Okay, up. You're going up, you're going to decrease. You're going down, what you're swimming through, depth. Is it D-E-P-T-H? I think it is. And the depth, okay, I think I misspoke. The depth of you and what you're going through. Smell. That's supposed to be W-I-N. What you're swimming through. And that's it. So if you think about it, E plus, you could just write something down like this. And just here. Oh, that's supposed to be gamma. So here, what the story is, I went down through that fluid that far. Then I went up through that far through that fluid. And then I went back down that fluid that far through that fluid. And then I arrived here at P1. That's all there is to it. There's nothing more to it. That's pretty much it. So all of these are the same. Let's see, does he have air there? He might have air in here, I don't know. He definitely has vapor here. Now, there's another thing, if it's a vapor, sometimes he'll do the vapor pressure. By the way, a vapor pressure equals the pressure of saturation. So you've seen that before. Just a different name. So that's pretty much it. I'll try to go back tomorrow. Let's see, I did that on the other day. So, how many of you are watching some of the other? Did I do the word of the day yet? Oh, I didn't. Oh, okay. Okay, so I got it there. I got to here. I'm in. Where is it? Oh, here it is. Okay. Okay, here. Oh, wait, come on. Wrong keyboard. Okay. Okay. Glob. I know it's not a word, but I like it. Glob. G-L-O-B, glob. The word of the day doesn't have to be a word. It can be any symbolisms of characters at all. And it can have any meaning we want it to. Yeah, it's extra credit because I didn't put it in the syllabus. So, and what I'm trying to do, this is a hard thing to do. I mean, we're going through some tough times. So I'm trying my best to adapt so that everybody has a chance at the lecture. So I thought the word of the day, if somebody's like out or something, they can go back in and put in the word of the day and at least give me some statistics that I can look to see, not individual tracking, but as a whole in the class where we are as far as the number of people who were, watching and stuff like that. So I picked it up from a guy who I think is in Conway, and he teaches math for an all online school. And he makes these little math things that are 10 minutes long. And then he's had good results with it. And he's I haven't seen the details, but he claims, the people who turn those in do really well. But he's teaching 8th grade. So it's a little different than here. But I thought, it's kind of a juvenile thing to do, but at the same time, if it's extra credit, you don't want to do it. Fine with me. So, well, I hate to let us go early, but I was wrestling a bear at 9 o'clock. I mean, literally in this room. I couldn't log in. Took off to computer services and spent an hour and a half with them. Oh. Yeah.
I always have to end up going up to the tech support and they'll unlock it.
Oh, that's what I ended up doing. Is that first door in the library?
Yeah, that's right.
Yeah. Well, they were apologetic, but we were trying to figure it out. And we finally figured out my phone kept beaconing and saying, I need to log in.
Oh. Really?
And so if you have your phone and it's beaconing and you change your password and you don't change it on the phone, so
Yeah.
It's
They'll
like,
start freaking out.
yeah. So I'm over here and I'm calling them on computer service. I got to even watch the stream and I'm like, what is wrong with this? This is stupid, you know. The poor guys, and they're just,
Yeah.
yeah.
Have a good day.
You too. Sure. Oh, I'm sorry. I got trouble. I need to get a magnifying glass.
You know, take my glasses off to the weeds and I can't see them doing that.
Yeah. Oh, that's because
It's really small and I'm not sure.
it probably will be too small. And specifically, this is because of that is water.
And it has 20 degrees where the space and space all take that.
Yeah. Yeah, even yeah, Google is fine. The only thing you've got here that's quick is he includes the mass of the can. It technically puts the pressure mass of the can out of the fluid. And you probably have done that, but and that's it, that's all you do.
Oh, and what, sure, I've been trying to watch videos, I have students in there that shut up.
Well, there's also, there's two sets of videos. There's the videos that are in the blackboard, and then there's the ones I produce in class. I almost think the ones that are on Blackboard are better, but I will give you, I will admit that I was very long-winded in those videos. And I probably rambled too much in those videos. Yeah, that's perfect. No, that's perfect. You just take a picture of that and shove it up to the blackboard and I'm happy.
Yeah. And old school, what is on my scanner,
Oh, do you?
scanning and all that.
Yeah, and I'm trying to be reasonable with everybody. I know it's, this last month has just been unbelievable with everybody.
First video, right after we come back, I was in contact with my brother-in-law's girlfriend. The second day because of COVID.
Oh, no.
So I had the quarantine for 5 days.
Oh, that's right, yeah.
No issues whatsoever.
Uh-huh.
On Sunday night, before I was supposed to come back, I get all symptoms and I got it.
Oh, no. But it must have been from, how did that happen?
No idea.
Wait a minute. Well, I just talked to a gentleman down there who had something similar, and he can't figure it out, and it's just like, I honestly don't know anything anymore. I'm just trying to make it through any given day. That's my goal.
I mean,